Hey there, Discrete Math. Welcome back. I hope everybody had a restful vacation, a coronacation, if you will. So today, now that we've wrapped up our apportionment unit, we have two more main units that we focus on for the rest of the year. We're getting into probability. Now, all of discrete math as a whole, really each piece is a little bit separate. It's discrete, if you will. There's all these different pieces to it. We've gone through graph theory, we've done money, we've done apportionment. Now we move into probability, and later on in the year, we close up with voting methods. Now, each different method, each different topic is separate, but the overarching goal of everything pulling things together is this idea of discrete math. There's a finite number of pieces. Today, we start looking at probability. And probability, perhaps we've seen a little bit before in statistics or in past experiences, it's the likelihood of something happening. So we're going to look through a little bit of the definitions, the notation, do a few examples. We start off kind of simple, but then we're going to build into how do we read statements. And a lot of probability is about how do you take a statement and turn it into something mathematical. So we're going to look through that today. And I'm going to switch over to our notes so you can have this, follow along, take the notes that you will, make certain that you get the definitions and the examples down, and then there's a little bit of practice to try out. So great to see you, even though I guess I'm not seeing you, but you're seeing me. Have you even made it this far in the video? How many of us have actually watched a full video all the way through? There's 26 of us in the class and 12 views. Really? Come on! You could do better than that. All right, I'll put another question for you in the classroom link as well, but here we go. So probability as a whole, it's looking at the experiments, it's the likelihood of something going to happen. Key words that we have going along. We start off, an experiment is something that happens in probability. So any procedure that is going to be repeated has a well-defined set of outcomes. You've seen this, we roll a die. When you roll a die, standard six-sided die, you get the numbers 1, 2, 3, 4, 5, or 6. We could have a deck of cards. We could have, I choose a grade at random, whatever it might be with probability. Now, when we roll a die, we get those different outcomes. Those outcomes are the results of the experiment. So when we roll a die, we get the numbers 1, 2, 3, 4, 5, or 6 for our standard six-sided die. Now, those specific values, we call those the results. Those are the outcomes, or the individual pieces, individual outcomes from an experiment. So we roll a 6. That's our the event that we might be looking for in our experiment. Now, our sample space is another word. It's the set of possible outcomes of an experiment. So here we're looking at the numerical. We started getting to a little bit of the mathematical language, a set, all the possible outcomes put together. So we might be looking at face cards when drawing a card from a deck, and that sample space would be a jack, queen, or king. As we move through probability, the notation that we're going to be using is something like this P within parentheses E. We would read this, the probability of event E. It's similar to your function notation from algebra, your f of x notation. So it's the probability of an event E. Now here, going to go on to the next page, the example that we have, computing probability. Get rid of that for now. We've got a box of chocolate candies, contains 25 pieces, 7 vanilla cream, 12 filled with caramel, the remaining 6 are filled with coconut. If we just close our eyes, shake up the box of chocolates, grab one out, what is the probability that it will be filled with vanilla cream? Well, the probability, the likelihood of something happening, so here we have the probability of event E, would be the number of successful outcomes out of the total number of outcomes. And when we're going through probability, it's always down to this formula. Everything that we do with probability, we set up what are the total of the number of successful outcomes, what are we desiring out of our total number of outcomes. So in this case, we're saying the probability that our chocolate, our candy, is vanilla cream. So probability of vanilla, P of vanilla. We would be looking for how many of the candies are vanilla out of the total number of candies. In this case, reading back, we have 7 are filled with vanilla, 25 total. So we have a probability of 7 over 25. That's what we're going to be looking for in probability. Now, we're going to be writing things, I'm going to be writing things in terms of fractions for the most part. We could go and change this into a decimal and have 0.28. We would have 28%. However, we can just leave it at 7 over 25. I'm not going to be particular about reducing or simplifying our fractions to the lowest possible denominators by removing any factors. I will write it out from time to time, but 7 over 25 works. I'm good with that. Let's take a look at the next example. So rolling a die, we think about our sample space, the numbers 1, 2, 3, 4, 5, or 6. We'll start off, that wasn't supposed to be everything all together. We've got the probability of rolling a 3. Well, we would think about how many sides of a die have 3 out of the total number of sides. Well, there is one side that's a 3 out of 6 total. If we look back at the sample space, there is 1 3 out of 6 possible options, so the probability of rolling a 3 is 1 out of 6. Probability of drawing an even number. I messed up these slides here. When we look at the total number of even sides of the die out of the total number of sides, notice that the total number of sides is still the same. There's still 6. But we look back at our sample space, all of the outcomes that we're considering, 1, 2, 3, 4, 5, or 6, well, we could have 2, 4, or 6 are all even numbers. There's 3 even numbers out of 6. Now, I mentioned earlier, 3 out of 6 is fine. If you're in the habit of reducing, simplifying your fractions to the least possible denominator, it's 1/2. But 3 out of 6 is satisfactory for us, or 0.5 if we revert to a decimal or a percentage. Each time, every single time when we're thinking about probability, it's the number of successful outcomes over the total number of outcomes. Probability of rolling a 4 or a 5. How many sides are 4 or 5? There's 2 out of 6, giving us 1/3. Rolling an 8. Well, if we go back, we don't have an 8 in our sample space. We can still do this probability, but the probability of rolling an 8, well, how many sides are an 8? There are 0. Well, 0 out of 6 is 0. That's never going to happen. No matter how many times you roll a die, you will never get an 8. On the other side, probability of rolling a number greater than 0. What number is greater than 0? 1, 2, 3, 4, 5, or 6? Well, that's all 6. That is a probability of 1, or 100%. Now, those two give us the extremes for our probability. Any probability we have must be greater than or equal to 0, or less than or equal to 1. You cannot have a negative probability. You cannot have a probability greater than 100%. If an event is guaranteed to happen, if it is certain to occur, if it will happen, the probability is 1, it is 100%. On the other side, if a probability of an event can never happen, we would say the probability is 0. Those two topics that we just looked at, rolling an 8 on a 6-sided die, or rolling any number greater than 0 on a 6-sided die, would be something that's never going to happen, probability 0, something that is guaranteed, probability 1. Move on to the next example. Now, cards are frequently used in talking about probability. At this point, I'm going to run through the different values that we could have with cards, outline the deck, and it's going to be expected that you can work with interpreting what is in a deck of cards. So just to highlight this standard deck of cards, there are 52 total cards. That deck, 52 total cards, is broken apart into 2 colors. There are red cards, there are black cards. It's completely divided in 2, so there are 26 cards of each color. Our colors are broken into suits. There are 4 different suits. There are spades, clubs, diamonds, and hearts. The spades and the clubs are black cards. The diamonds and the hearts are reds. So if there are 4 suits out of the 52 total cards, that means there are 13 cards in each suit. So there are 13 spades, 13 clubs, 13 diamonds, 13 hearts. In each suit, we have 13 different ranks or values, as we call them, 13 different cards that we have. That would be our ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, and king. Specifically, those jack, queen, and kings are face cards. The ace is not a face card, but jack, queen, king. Those are the 13 different ranks or values. There is one of each of those per suit. So we have 4 cards of each rank, 1 per suit. So there is an ace of spades, an ace of clubs, an ace of diamonds, an ace of hearts. We've got those different values. We can use this to illustrate or demonstrate different probability problems. For example, probability of drawing an ace, I got it right, we would want to know how many aces are in a deck out of the total number of cards. So I'm going to go back up to that last statement. There are 4 cards of each rank, 1 per suit. So we have 4 aces out of 52 total cards. Now we can just leave it as 4 out of 52. That's satisfactory for me. Or we can divide that common factor of 4, reducing our fraction to least possible denominator, saying that's 1 over 13. Next, probability of drawing a heart. Well, how many hearts are in a deck? We think about the total number of hearts divided by the total number of cards. Well, there are 13 different ranks per suit, so that means there are 13 cards per suit. There are going to be 13 hearts in a deck out of 52 total cards. We'd have 13 over 52. Or thinking, I want a heart, well, that's a specific suit. There are 4 different suits, so I could say there's 1 suit that I want out of 4 suits total, or 13 cards out of 52 total cards. Moving on, a king or a queen, I would need how many total kings and how many queens altogether there are out of our total number of cards. So I would need the sum of our kings and queens. Now there are 4 kings and 4 queens in a deck out of 52 total cards. So we have the 4 kings, 4 queens. Together we have 8 cards that we are looking for out of 52, which gets us 2 specific cards out of the 13 different ranks that we have available. So we can just leave it as 8 out of 52, or you can reduce it to 2 out of 13. Either way is satisfactory for us. Skip this one for a moment. Rolling 2 dice. We often have to think about the different possibilities because more than one thing is happening. When we talk later on about compound probability, multiple things happening. If we are rolling 2 dice, well, we could have the value on the first die, the value on the second die. Quite frequently, we talk about the sums, the products, or different combinations of the 2 die. Here I'm saying 2 dice are thrown. Now notice there are 6 values for 1 die. There are 6 values for total. When we look at all the combinations, we could get a 1 and a 1, a 1 and a 2, a 1 and a 3, so forth. We could get a 2 and a 1, which is different from a 1 and a 2. 2 on the first die, 1 on the second die, or 2 on the second die, 1 on the first die. Those are completely separate, so we would count those separately. There are 6 options for the first die, 6 options for the second die, and when we draw out all the possibilities, we have 36 different outcomes. Going to the example, well, we want to roll a sum of 6. So we look for how many 6s can we possibly get out of the total number of sums. As just mentioned, we have 36. Now we get that by multiplying. You can get a 1 and a 1, 1 and a 2, 1 and a 3, 1 and a 4, etc. Or a 2 and a 1, 2 and a 2, 2 and a 3. There are 36 total different ways. How many of these are 6? When we look, okay, 5 and 1, 4 and 2, 3 and 3, 2 and 4, 1 and 5. There's 1, 2, 3, 4, 5 different ways out of 36 total. How many ways can we get a 12? Well, we look for the number of 12s that are possible out of the total number of sums. Well, again, there are 36. We look for the 12s. The only way we can get a 12 is a 6 plus 6. So there's 1 way out of 36. So using a chart listing all the possibilities is one way of making certain that we have met our full sample space. The total number of outcomes, there are different strategies that we need to think about. I'm going to go back to the previous example. We're going to flip a coin 4 times in a row. What is the probability that we get exactly 1 head? So we're going to use what's called a tree diagram to visualize our sample space. We've got 4 different coins here, so we've got to do a little bit of work. How many different outcomes are there? On the first coin, we've got to either get a head or we could get a tail. Now here I'm going to start breaking things apart. There's the first coin. We get a head or a tail. If we get a head the first time, we could get a head the second time, or if we get head the first time, we can get tails the second time. So here we're going to systematically expand and make a list of all the possibilities in this experiment. If we get a head the first time and a head the second time, the third coin we can get a head, or we can get head the first time, head the second time, tail the third time. Each time we're expanding this. If we get a head the first time, head the second time, head the third time, we could get heads the fourth time. Or if we get heads, 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 we could get tails for the fourth throw. Those are all the possible options if we get heads, heads, heads. Well, heads, heads, tails, if we flip heads, then tails, we could get heads for the fourth coin. Or heads, heads, tails, we could get tails on the fourth time. If we get heads, then tails, we could flip a heads. Or let's just keep on expanding this. We get heads, tails, we get tails on the third toss. If we get heads, tails, heads, we get heads. If we get heads, tails, heads, we can get tails. If we get heads, tails, tails, we can get heads, or we get heads, tails, tails, tails. If we get tails the first time, you can see you're going to keep on expanding this. Notice what I'm doing is I'm going to keep changing just one value at a time, looking for all the possibilities. We're going to have just the exact opposite of this now. We're going to have tails, heads, heads, heads. We'd have tails, heads, heads, tails. We could have tails, tails, heads, heads. We could have tails, tails, heads, tails. We could have tails, 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 heads. We could have tails, 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 tails. Notice we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I am missing 2. There should be 16. Oh no! What did I do wrong? Uh-oh. Here's why we listed out. Here's why I really miss being in a classroom, because this is a lot easier to do. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Uh-oh. What do we miss? I hate typing this stuff out. Got that one. Got that one. Tails and heads, heads, heads. Heads, tails. Heads, tails, heads, 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 tails, tails, heads, tails, heads, heads. Heads, tails, heads, 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 tails. Tails, heads, heads, tails, tails, tails. 2, 3, 4, 5, 6, 7, 8. We should have just the exact opposite for the tails. So looking at the bottom here and the top, we can figure this out. Okay, those are all tails, those are all heads. All tails, last one's heads. All heads, last one is tails. Third one is heads. Third one is tails. First 2 and second 2. First 2, second 2. All right, the middle 2 are heads. The middle 2 are tails. We've got the last 3. I think we missed this. So in between there, let's go. We are missing tails, heads, tails, tails. Do we have that one? No, we don't. And tails, heads, tails, heads. Is that used already? No, that wasn't. So there's 16 different ways to do that. Troubleshooting, trying to figure it out. Making a list, checking it twice. We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 different ways of doing that. The probability we wanted. Suppose you flip a coin 4 times. What is the probability that you would get exactly one head? Well, our probability, we're going to say, of one head, exactly one head, it's the number of heads out of the total. So the total, we're going to be out of 16 different ways to do this. How many of these in the list have exactly one head? Here's one. Here's one. Here's one. So there are three that have exactly one head. That's not right. It should be 4. So we've got that one, that one, that one, that one. All right, there's 4 of them. And what I was thinking about is, well, the first coin could be head, the second coin could be head, the third coin could be head, the fourth coin could be head. So there's 4 different ways that we can have exactly one head, giving us 4 out of 16. So there's our start to probability. There's a few problems up on the classroom site. Try it out. Good luck.